Hello everybody and welcome to this video on matrix chain multiplication. Matrix chain multiplication is an optimization problem regarding the most efficient way to multiply a given sequence of matrices. So we have a number of two-dimensional matrices and we want to minimize the number of multiplications needed by finding the best order or arrangement of parentheses. So we don't need to perform the actual multiplications themselves. Instead, in this scenario, we are concerned with the number of multiplications being calculated. So if we want to know how to calculate the number of multiplications, we're going to first need to remind ourselves on how we calculate the resulting size of a matrix. So say we have two matrices, M1 and M2. Multiplied together, they make a new matrix M3. So for example, matrix 1 might be of size 3 by 2, matrix 2 could be of size 2 by 4. So the resulting size of matrix 3 is going to be 3 by 4. We can visualize this looking at matrix 1, so we can see that it's got 3 rows and 2 columns, and then matrix 2, multiplying it, we can see that it has 2 rows and 4 columns. Then the resulting matrix, matrix 3, is going to have 3 rows and 4 columns, and we can see this in how we formally multiply matrices together. We can see how we get the resulting number of cells all the way until we have a matrix of size 3 by 4. So now we need to know how to calculate the number of multiplications that we perform when multiplying two matrices together. So we can use the previous example of M1 times M2, which is equal to a resulting matrix M3. For visualization purposes, we can fill the matrices with dummy data and we can see how many multiplications we actually need to perform to get the resulting matrix M3. It's 24 in this scenario, but we don't actually need to physically calculate the multiplications, and we don't need to fill the matrices with dummy data. There's a quicker way to get to the number 24 in this scenario. We can calculate it by the number of rows in the first matrix times by the number of rows in the second matrix times by the number of columns in the third matrix. Now, if you notice, this is basically the resulting size, 3 by 4, times by the linking number. Now, the linking number is the number that is the same for matrix 1 and matrix 2. And this, in this example, is 2. So that allows us to multiply the two matrices together, because the only way you can multiply two matrices together is if the number of columns in the first matrix is equal to the number of rows in the second matrix. So this is, we can call this the linking number, being 2 in this scenario. We then multiply 2 by the resulting size of matrix number 3, which is 3 by 4. 2 times 3 by 4 equals 24. So that's a quicker way that we can get to the resulting number of multiplications. So now we know how to calculate the number of multiplications. We're going to have scenarios where we're multiplying lots of different matrices together in different arrangements, and those arrangements are going to give a different number of multiplications. Now, in this problem, we want to find the most efficient arrangement of matrices multiplied together in a certain order, whereby it gives us the smallest number of multiplications, trying to make the calculation as efficient as possible. So let's take an example. We've got matrix 1, matrix 2, and matrix 3 of size respectively 2 by 2, 2 by 3, and 3 by 4. So if we look at this specific arrangement where we're multiplying matrix M1 by M2 first, and then the result of that is then multiplied by matrix 3. We can use the previous knowledge that we gained from the previous slide about how to calculate the number of multiplications, which was the resulting size of the matrix times by the linking number. Now, focusing on firstly matrix 1 multiplied by matrix 2, the linking number in this scenario is going to be 2. That's the number that allows us to multiply matrix 1 by matrix 2, because it is the number of columns in matrix 1 times the number of rows in matrix 2. And I should be able to show here. Yeah, so it's the number of columns here times by the number of rows here. So this allows us to have a valid matrix multiplication. So the resulting size of the overall matrix is going to be 2 by 3. And then we're going to times it by this linker number, which is going to be 2. So we can see that calculation here. And that's going to give us 12 multiplications in total. So now we have a new resulting matrix. If you remember from the previous slides, we had called that M3 and it was in the color white. This is basically the same thing. So we now have a new resulting matrix of size 2 by 3. So we're going to want to then multiply this by matrix M3. And we can actually do that because our resulting matrix has 3 columns, which works out well because we can then times that by the 3 rows of matrix M3. This is then going to give us a resulting size of the overall calculation of 2 by 4, the linker number between our resulting matrix for inside these parentheses here, and matrix 3 is going to be 3. So we can then multiply these together to get the number of multiplications overall. For the overall calculation, we're then going to need to add that to the number of multiplications for this previous multiplication. So we're doing it for both. We'll add those together, and then we get the number of multiplications overall that we needed to complete for that specific arrangement of multiplying these matrices together, which is 36. We can then take a different scenario whereby first we're multiplying matrix 2 by matrix 3, and then the result of that is then multiplied by matrix 1. So in this scenario, we're first going to multiply matrix 2 by matrix 3. This is possible because matrix 2 has 3 columns and matrix 3 has 3 rows. So we can multiply these two together. The resulting size of matrix 2 times matrix 3 is going to be 2 by 4. We can then times that by the linking number, 2 times 4 times 3, which is going to be equal to 24. We now have a new resulting matrix of size 2 by 4. And that resulting matrix of 2 by 4 is then going to multiply onto matrix 1 of size 2 by 2. So the linking number here is going to be 2 because we have 2 columns and 2 rows in the resulting matrix. So the linking number is going to be 2, and the overall size of the new matrix is going to be of size 2 by 4. So we're going to times that by the linking number. 2 times 2 times 4 is equal to 16. We then, as previously done, add the number of multiplications needed for the overall matrix by the number of multiplications needed for the first multiplication, which was matrix 2 times matrix 3, so 16 plus 24. This is equal to 40. So you can see how the number of multiplications is different for this arrangement compared to this arrangement. So the number of multiplications depends on how we're multiplying the matrices together. Now, in this scenario, there wasn't much of a difference, but you can imagine if we have a lot of different matrices, so say we have hundreds of different matrices in lots of different orders, then the difference in number of multiplications is going to become even greater. So it's going to be even more vital that we solve this problem correctly, where we find the most efficient arrangement to save time and increase efficiency. So we can look at a variety of approaches on how to solve this problem. So we can look at the recursive approach, which is solving the overall problem by solving smaller instances of the problem and then calling these instances, starting at the final solution and then looking at what sub-problems that solution depends upon. So say we have three matrices, we're going to want to store the dimensions of the matrices, because that's the bit we want to focus on to calculate the number of multiplications, in an array. So an array called P. So for example, at position 0, P is storing the first row of the first matrix, and then at position 2, it's storing the linking number between matrix number 2 and matrix number 3. So we're going to have a number of variables in this recursive solution. So K is going to be the split, so where we're going to split the multiplications of the matrix. So it's going to be a way that we can formalize the arrangement of how we're multiplying them. So for example, if K was 1, we can see that we're sort of multiplying M1 by M2 times M3. And if K is 2, we're sort of splitting it here, so we're multiplying M1 times M2 first, and then multiplying that result by M3. And then I and J will be variables that we can use to iterate through the possible combinations of each split. And then we're going to calculate for each K the minimum count, so the most efficient arrangement for that specific split. So for example, when we're multiplying these different matrices, we've got a number of different splits, and you can see, say if we have 4 matrices, we're going to have a lot of different possible scenarios and arrangements for different splits in how we add the parentheses to these different matrix multiplications. So let's have a look at the recursive algorithm actually with an example to get an idea of how it works. So this is the code that we're going to be using. So we're going to be first calling the overall final solution, which is going to be the full range of matrices multiplied together. So P is going to be an array storing all of the dimensions of all of the different matrices, and then we're going to be going from a range of 1, so we're going to be starting at the first matrix, and we're going to be going all the way to the last matrix, which is defined here as the size of the array minus 1, because the number of dimensions for each matrix is 2, so we're going to always have one more dimension than we have matrices. So we know that 1 minus the number of dimensions that we've got is going to be equal to the number of matrices. So for example, if we had 4 matrices, which we're going to have in this example, it's going to say we're going to take an array of the dimensions of all of these matrices. We're going to be going from a range of 1 up to 4 matrices. So we then go into the actual function itself. We've got the base case here, which is saying when I is equal to j, so when we have a matrix by itself, if you multiply a matrix by itself, that's not going to result in any multiplications. That's going to be 0, so we can then return 0. We're then initializing the minimum variable as a very large number, so that when we do start looping through, the minimum can then be updated for the first iteration, which is going to be always smaller than this very large number. And then we have a count, which is going to be the number of multiplications. This is the main for loop here. So K is going to be the different splits, so the different possible ways that we can add parentheses to the different multiplications, and then I and J are going to be the different combinations within those different splits, and this is going to be adding the different possibilities together to get the overall number of multiplications. So let's have a look at an example. So we have here 4 matrices, and these are their different dimensions, and each dimension is then going to be in a specific place within the P array, and then we're going to be multiplying these different matrices together. Now we're going to have a lot of different arrangements for how we're going to be multiplying them. In this specific scenario, because the recursive algorithm is fairly inefficient compared to other solutions. We're only going to be looking at the first layer of arrangements. So we're going to be looking at one specific scenario of multiplying all 4 of the matrices together. If we did all of them, then it would probably take too long, but it's just more for sort of demonstration purposes as opposed to getting the actual answer. Then when we move on to more efficient approaches later on in the video, can show the actual full answer and the best possible arrangement of parentheses. But as we're going through it step by step, that would take far too long, which is a good indication that the recursive algorithm isn't the best possible way to approach this, but it's good to see how it can be solved in a recursive manner. So the first thing we're going to be doing is looking at all 4 matrices, and we're going to be looking at this specific scenario. So we're not going to touch upon scenarios where we're doing matrix 1 times matrix 2 times matrix 3 times matrix 4, so if brackets were here and here and here and here, and we're not going to be looking at a scenario, say, where we multiply matrix 1 by matrix 2 by matrix 3 first, and then we times that all by matrix 4. We're just going to be looking at the specific top level case of whereby we're multiplying matrix 1 by the result of matrix 2 times matrix 3 times matrix 4. And we can see even for this specific top level iteration, it takes a while because we have to go through all of the possible subproblems of each range of matrices. So you can see for this range, so we're starting from matrix 1 and we're going to matrix 4. So this is the final matrix. You can see that we already hit the base case because we have a matrix by itself, M1, so M1 times by itself is obviously going to return 0, so that's going to be a base case hit. And then we're going to be looking at the subproblem whereby we need to know the smallest number of multiplications for matrix 2 times matrix 3 times matrix 4. Now that's basically the same as this problem, which is matrix 1 times matrix 2 times matrix 3 times matrix 4. It's just a smaller subproblem. So we're going to be calling this function again, but we're going to be calling it, instead of 1 here, we're going to be calling it with 2. So it's going to be 2 by 4, so we're going to be looking at a smaller range. So we're going to sort of move into this subproblem. And you can see this subproblem also contains other subproblems. So this subproblem in itself contains a subproblem of we don't know how many multiplications it would take to times matrix 3 by matrix 4. And we know that times the matrix 2 by itself is just going to be a base case hit. I probably should have put the brackets are here, but in this scenario we're doing matrix 3 times matrix 4 first, and then we're multiplying it by matrix 2. So to get this, we then need to work out this subproblem, matrix 3 times matrix 4. So to work that out, that's 2 separate cases whereby we're hitting the base case each time. Matrix 3 times by itself, matrix 4 times by itself, that's going to be 2 base cases. That's going to result overall in these 2 specific calculations being 0. So we're just going to be focusing on this specific part of the formula, which is going to be working out the number of multiplications. And the only thing that's going to be taken into consideration is the size, because we haven't got any additional multiplications that we need to add on top of that because it's only 2 matrices. So in this example, the number of multiplications is going to be 24. And we can see now we have our first combination within K complete. So we know for this specific range from matrix 2 to matrix 4 that times in matrix 3 by matrix 4 first and then times it by matrix 2 is going to give us a number of multiplications of 60. However, we still have another scenario that we haven't yet thought about. We need to think about times in matrix 2 by matrix 3 first and then times in it by matrix 4. So we're going to now do that. And you can see that we get to a scenario where we're going to hit the base case. So the base case is going to be matrix 4 by itself this time, because we're times in matrix 2 by matrix 3 first. So we then need to call the function again just with M2 and M3. And when we do that, we're then going to see that the number of multiplications for this is going to be smaller. It's going to be 42. So we now know for this range, we've tried all possible combinations, and the best way to arrange the matrices for this specific scenario is to do matrix 2 times matrix 3 first and then multiply it by matrix 4. That's going to give us the minimum of 42 multiplications, as opposed to doing matrix 3 times matrix 4 first and then multiplying it by matrix 2, which gave us 60 multiplications. So based on this bit of code here, we're only going to be keeping 42. So we now know the answer to this subproblem, which is then going to help us figure out the next part of the solution. Because we now know this part of the subproblem, so we're sort of unwinding in the recursion. We've gone through all of the different subproblems, we've hit all the possible base cases, we've then got to scenarios where we do actually know the answer and we aren't calling functions. We're then unwinding back and getting to a scenario where we're filling in the gaps and we know the number of multiplications for different subproblems, going up towards the final subproblem and this final specific combination, whereby we know that in this scenario where we're times in M1 first and then times in M2 by M3 by M4. Sorry, we're times in M2 by M3 by M4 first and then times in it by M1. We know in this scenario that the minimum is going to be 60. Now, I should point out it's kind of confusing, but we did have a scenario where the minimum was 60 before, where we were looking at this specific range. But this minimum 60 is for the new resulting matrix for this combination. Now, this is where I'm going to leave it here for the recursive algorithm, because otherwise we'd then have to do this these calculations another 2 times to work out if 60 was the smallest combination, or if times in M1 by M2 and then times in M3 by M4 is smaller than 60, or if times in M1 by M2 by M3 first and then times it by M4 is smaller than 60. And to do that, you then need to go through all of the possible subproblems once again. So you'd need to call all of the different subproblems. Then eventually you'd get the subproblems would fill in the numbers, and then you'd unwind, and then you'd finally get the answer. But you can see that it's taking quite a long time because we're having to go through all of the different subproblems again. And there'd be scenarios where we're repeating subproblems that we already know the answer to. So this isn't the most efficient solution, but it gives you an idea of how you could complete matrix chain multiplication using a recursive approach. Instead, we can use a dynamic programming approach, which uses a bottom-up approach to calculate each subproblem first, storing the subproblem in a memorization table so we know the answer to it already. Then, if the subproblem reoccurs later on, further up the tree, we can then retrieve the answer of the subproblem from the memorization table, rather than having to compute the subproblem again, which then may contain more subproblems, so this could take a long time. Whereas if we've already computed the bottom subproblems, then this can help us move in further up the tree. So as we continue to calculate the subproblems, we then put them in the memorization table. Then if they reoccur later on, we already know the answer. So that helps us improve the efficiency. You can see here that the time complexity of the recursive algorithm is big O of 2 to the n. in the worst case. And that's because for each pair of matrices, the recursive function may branch into multiple subproblems, leading to an exponential growth in the number of recursive calls. The worst case space complexity for the recursive approach is big O of n, because the recursion may need to keep calling all the way down to a depth of n, and then it would need to keep track of n values. These values could be the number of multiplications. We can see an improvement in the dynamic programming approach. The worst case time complexity goes down to big O of n cubed, because for each range in the memorization table of size n squared, we need to calculate n possible splits. The worst case space complexity would be big O of n squared, because both the table storing the optimal number of multiplications for each range and the corresponding optimal split position are both of size n squared. So because they're both of size n squared, that is the highest order term, so it's big O of n squared. So you can see an improvement in the efficiency of the solution using dynamic programming. We can have a look at the dynamic programming approach in practice. So we're going to use the same matrices as before with the same dimensions, these dimensions stored in the P array as before. We then have a table which we're going to use for memorization, M, which is going to store in it the subproblems. So in this scenario, the subproblems are going to be the different ranges in which we're calculating. So for example, range 1 to 3 might be from matrix 1 to 3, and we know the minimum number of multiplications for that specific subproblem, and then that would get stored in the table M. S will allow us to know the arrangement of parentheses after we've calculated all the subproblems, because we can then go back and see where was it where we had the minimum number of multiplications, where was it where we actually put the split of k. So here we're defining that in table M, if the number of rows is equal to the number of columns, then that cell is going to be equal to 0, because that means that the matrix is multiplied by itself, which is not going to result in any multiplications. So the number of multiplications is going to be 0 for that subproblem. And then here we're just going through all of the different splits and their possible combinations, and the same as before, calculating how we get the number of multiplications. So we can see these tables here. So M, as I said earlier, is going to store the subproblems, the minimum number of multiplications for each specific range within the main problem that we're trying to solve, the main multiplication, and S is going to store the minimum number of multiplications, the split of where it's going to be. So following the algorithm, we can add zeros on the diagonal. We can have a look at the first subproblem. So you can already see that this is different to the recursion. We're not starting from the top, we're not starting from M1 all the way across to M4, we're just starting with a small subproblem. What is the minimum number of multiplications for matrix 1 times matrix 2? That's going to be 24. So we can add that into our table here. So we now know that. So if we're then going to be using that in another subproblem, we can then just take that answer. We don't need to recalculate that specific range. We can see here that the split is just going to be in between these two. And that's fairly self-explanatory, because that's the only possible split that we can do in that scenario. But when we get to bigger ranges, there's going to be possibilities, different possibilities. So for example, if we were doing matrix 1 times matrix 2 times matrix 3, we could have a split of down the middle here or down the middle here. So k could either be 1 or 2. So, and then we just pick whichever one is going to give us the minimum number of multiplications, and then add that to the S table. So we're then just doing another subproblem. So this is the smaller subproblem that we could do. Well, technically we did do the smaller subproblems, which are just the matrices themselves, but that's all going to be 0. So now we're moving on to a range of 2. So we're multiplying all the different ranges of matrices where it's just 2. So we can see that one's 24, and that one's 2, and that one is also actually 24, funnily enough. These could obviously be different or the same, but we get a scenario where we're multiplying m1 by m2, m2 by m3, m3 by m4 in pairs. They're all going to be 24, and this is just going to be 1, 2, 3. Now we have the answer to the subproblems. We can use it in a different, bigger subproblem. We can now move on to a range of 3. So L here in the code just keeps track of the range of how many matrices we're multiplying together at once. Looking at this range, so we're multiplying from matrix 1 to matrix 3. We need to try different combinations for this, because there's going to be 2 combinations in this scenario. So we need to multiply matrix 2 by matrix 3, and then the result of that by matrix 1 in this specific combination. We can see that we can use subproblems that we've already calculated in our calculation, rather than having to recalculate everything again. So that gives us an answer of 36. This is stored in the variable q, because we haven't looked at all the possible combinations yet for this range. So we might have one that's even smaller than that. So we just keep it in q for now until we've considered all the possible combinations. We then consider the other combination, whereby we multiply matrix 1 by matrix 2 first, get the resulting matrix, and times that by matrix 3. You can see we can use the subproblems again, and we get an answer of 40. Now 40 isn't smaller than 36, so after trying all the possible combinations, q is equal to 36. So we know for the range of 1, 3, so between matrix 1 and matrix 3, the minimum number of multiplications is 36. And we know that when we did this, we were timesing matrix 2 by matrix 3 first, and then multiplying that by matrix 1. So the split was down by just after matrix 1. So we know that the split comes here, and that can be added to the S table. We now need to look at the other range of multiplying 3 matrices together, which is between 2 and 4. We can try out the different possible combinations again. We can use the subproblems that we've already calculated to get the answer of 60 for this combination. So q is updated at 60 for this range. We can then try the other combination using the subproblems. We can see that we get 42. This means that 42 is now the minimum for this specific range, and we can add that to our table. We see in this scenario that the minimum number of multiplications was at a split just after matrix 3. So we add that to our S table. We can now move on to a range of 4. So we're considering all 4 possible matrices multiplied together. And you can see the first possible combination is the one that we tried for recursion, and we did get a solution. We got 60 for the recursion, and we get the same here for dynamic programming. The thing is, we can calculate this so much quicker using dynamic programming. It only takes us 3 additions. Whereas for the recursive solution, think back to that previous slide where we were doing a lot of computation, a lot of different subproblems going all the way to the bottom to find all of the different little subproblems and then computing and unwinding back up. You can see how much more efficient this dynamic programming solution is. So for this first combination from matrices 1 to 4, we get 60, so we update q to be 60 for this specific range of L equals 4. We then look at the next combination, and we can see that it gives us 72, which is bigger than 60, so this isn't more efficient, so we continue, and we don't update q. We then look at this combination, which is multiplying matrix 1 by matrix 2, matrix 3 first, then the result of this multiplied by matrix 4. This gives us a result of 48, which is smaller, so more efficient than the previous combination that we had, which was q equals 60. So we update q to be 48. We then add this to the table for the range 1 to 4, and we can see that we're splitting just after matrix 3 here. So we can add that to our split table S for the range 1 to 4. So we can see that's 3. From this, we have the full complete table for S, which means we can then figure out the best possible combination of parentheses to give us the most efficient solution, the least number of multiplications. So we can see here, from matrices 1 to 4, from the range 1 to 4, we need to first split according to the S table just after matrix 3. So then this gives us our first set of parentheses. We now, inside the first set of parentheses, have a range of matrix 1 to matrix 3. So we look at the S table. From range 1 to 3, it tells us to split after matrix 1. So we do that, we split down here, and then we have our second set of parentheses around matrix 2 to matrix 3. So the best possible combination for these four matrices is to multiply matrix 2 by matrix 3 first, the result of this multiplied by matrix 1, then the result of those two multiplied by matrix 4. This gives us the most efficient solution and gives us the least number of multiplications when multiplying these four matrices together. Now we've seen how to find the optimal arrangement of parentheses to get the minimum number of multiplications. Matrix chain multiplication could be used in a variety of applications in real life, such as circuit design. Circuits can be modeled using matrices, and matrix chain multiplication helps optimize how these matrix calculations are performed, improving the efficiency of circuit design and operation. It can also be used in computer graphics. Transformations such as scaling, rotation, and translation are often represented as matrices. Multiple transformations need to be applied to objects in complex scenes, which can be modeled as a matrix chain multiplication problem. Efficiently multiplying these transformation matrices can help improve the efficiency of the rendering process. It can also be used in camera calibration. Parameters can be represented as matrices in camera calibration. Matrix chain multiplication can be used to improve the order of these matrix operations and thus improve the efficiency of the calibration. And that concludes this video on matrix chain multiplication. Thank you for watching.